Good morning, students. In the previous video, we understood packing, voids, and packing density. Today, we will understand about the defects. Defects can be adulteration or everything that we have expected cannot be obtained. In solid, if the arrangement is not what we expected, then it is called defect. In universe, there exists no ideal crystal without defect. In order to avoid effects, the process of crystallization is conducted at extremely slow rate. However, even after the crystals are obtained, is not free from defects. These defects in solid are classified into two: point defect and line defect. Point defects are the irregularities or deviations from the ideal arrangement around a point or an atom in a crystalline substance, whereas line defects are the irregularities or deviations from the ideal arrangement in entire rows of lattice point. Now you can see further classification of point defect in impurity defect, stoichiometric defect, and non-stoichiometric defect. Impurity defect, when there is a presence of foreign atom, ion, or molecule, the defect is known as impurity defect. Stoichiometric defect. A stoichiometric defect is a defect by which there is no disturbance in the stoichiometry of the solid. It is further classified into Schottky defect, Frenkel defect, vacancy defect, interstitial defect. Next is non-stoichiometric defect. The defect that causes the ratio of the number of cations to anions to be different from that indicated by the ideal chemical formula is known as non-stoichiometric defect. It is further classified into metal axis defect and metal deficiency defect. Let's discuss about point defects. First is stoichiometric defect. These are the point defects that do not disturb the stoichiometry of the solid. They are also called intrinsic or thermodynamic defects. Basically, these are of two types: vacancy defects and interstitial defects. Vacancy defect, when some of the lattice sites are vacant and the crystal is said to have vacancy defect. This results in decrease in density of the substance. This defect can also develop when a substance is heated. Next is interstitial defect, when some constituent particles, atoms or molecules occupy an interstitial site or vacant site, the crystal is said to have interstitial defect. This defect increases the density of the substance. Vacancy and interstitial defects, as explained above, can be shown by non-ionic solids. Ionic solids must always maintain electrical neutrality. Rather than simple vacancy or interstitial defects, they show these defects as Frenkel and Schottky defects. So, Frenkel defect. This defect is shown by ionic solids. The smaller ions, usually cation, is dislocated from its normal site to an interstitial site or void. It creates a vacancy defect at its original site and interstitial defect at its new location. Frenkel defect is also called dislocation defect. It does not change the density of the solid. Frenkel defect is shown by ionic substance in which there is a large difference in the size of ions, for example, ZnS, AgCl, AgBr, and AgI due to small size of Zn2 positive and Ag positive ions. Now, Schottky defect. It is basically a vacancy defect in ionic solids. In order to maintain electrical neutrality, the number of missing cations and anions should be equal. Like simply vacancy defect, Schottky defect also decreases the density of the substance. Number of such defects in ionic solids is quite significant. Schottky defect is shown by ionic substances in which the cation and anion are almost similar size. For example, NaCl, KCl, CSCl and AgBr. It may be noted that AgBr shows both Frenkel as well as Schottky defects. So this is all about stoichiometric defect, a defect by which there is no disturbance in the stoichiometry of the solid, either it is ionic or non-ionic. Now we will understand impurity defect. When there is a presence of foreign atom, ion or molecule, the defect is impurity defect. Like if molten NaCl containing a little amount of SrCl2 is crystallized, some of the sites of Na positive ions are occupied by strontium ions. Each strontium replaces two Na positive ions. See, this is impurity defect. It occupies the site of one ion and the other site remains vacant. The cationic vacancies thus produced are equal in number of that of strontium ions. Another similar example is the solid solution of cadmium chloride and AgCl. Now, non-stoichiometric defect. As I mentioned earlier, the defect that causes the ratio of the number of cations to anions to be different from that indicated by the ideal chemical formula is known as non-stoichiometric defect. It was divided into metal excess defect and metal deficiency defect. So first we will understand metal excess defect. Alkali halides like NaCl and KCl show this type of defect. When crystals of NaCl are heated in an atmosphere of sodium vapor, the sodium atoms are deposited on the surface of the crystal. The chloride ions diffuse to the surface of the crystal and combine with Na atoms to give NaCl. This happens by loss of electron by sodium atoms to form sodium ions. The released electrons diffused in the crystal and occupy anionic sites. As a result, the crystal now has an excess of sodium. The anionic sites occupied by unpaired electrons are called F centers or Farabi centers. They impart yellow color to the crystals of NaCl. The color results by the excitation of these electrons when they absorb energy from the visible light falling on the crystal. Similarly, excess of lithium chloride, lithium makes crystal pink, and excess of potassium makes potassium chloride crystals violet. This is metal excess defect due to anionic vacancy. Next is metal excess defect due to presence of extra cations at interstitial site. Did you notice that ZnO, zinc oxide, get hot and changes its color? Zinc oxide is white in color at room temperature. On heating, it loses oxygen and turns yellow. On heating, zinc oxide convert into zinc ions with liberation of oxygen and 2 electrons. Now there is excess of zinc in the crystal and its formula become Zn1 plus XO. The excess zinc ions move to interstitial sites and the electrons to the neighboring interstitial sites. Next is metal deficiency defect. There are many solids which are difficult to prepare in stoichiometric composition and contain less amount of the metal as compared to the stoichiometric proportion. Typical example of this type is FeO, which is mostly found with the composition of Fe 0.95O. It may actually range from Fe 0.93O to Fe 0.96O. In crystals of FeO, some Fe2 positive cations are missing and the loss of positive charge is made up by the presence of required number of Fe3 positive ions.
If the constituent particles, such as atoms, ions, or molecules, in a solid crystal are arranged in a regular fashion, then the crystal is said to be an ideal or perfect crystal. However, no crystal in the universe is perfect. Almost all the crystals encountered in practice suffer from defects. This happens when the crystallization process occurs at a fast or moderate rate. In order to avoid these defects, the process of crystallization is conducted at an extremely slow rate. However, even the crystals so obtained are also not free from defects. These defects in solids are broadly classified into point defects and line defects. Point defects are the irregularities or deviations from the ideal arrangement around a point or an atom in a crystalline substance. These may arise in a crystal due to one of several reasons: the absence of a constituent particle, the presence of a foreign particle at the lattice site, the presence of a foreign particle at the interstitial site, the displacement of a particle to the interstitial site. Point defects are classified into three types, namely stoichiometric defects, non-stoichiometric defects, and impurity defects. Let's first learn about stoichiometric defects. A stoichiometric defect is a defect by which there is no disturbance in the stoichiometry of the solid. These are also called intrinsic or thermodynamic defects. Stoichiometric defects are further classified into vacancy defects and interstitial defects. The defect in which a constituent particle is missing from the crystal lattice is known as a vacancy defect. This defect develops when a substance is heated. You can clearly observe from this figure that some of the constituent particles are missing from the crystal lattice. As a result, some vacancies are created. The major consequence of a vacancy defect is that the density of the substance decreases. On the other hand, an interstitial defect arises when some of the constituent particles occupy the interstitial sites in a crystal lattice. From the figure, it is evident that some constituent particles occupy the interstitial sites in a crystal lattice. As a result of this defect, the density of the substance increases. This holds good only for non-ionic solids. Ionic solids must always maintain electrical neutrality. Rather than a simple vacancy or interstitial defects, ionic solids show Frenkel and Schottky defects. Now let us learn about Frenkel defects and Schottky defects. A Frenkel defect is caused if some of the ions of a lattice occupy the interstitial sites by leaving a corresponding number of normal lattice sites vacant. You can see this from the figure here. This creates a vacancy defect at the original site and an interstitial defect at its new location. A Frenkel defect is also known as a dislocation defect. It does not influence the density of the substance. This type of defect occurs in compounds with ions of different sizes. Since cations are smaller than anions, cations can easily fit into the vacant spaces in the lattice. For example, in a silver chloride crystal, an Ag+ ion occupies an interstitial site by leaving a vacancy at the original site. Zinc sulfide, silver bromide, and silver iodide are other examples that have Frenkel defects. A Schottky defect is caused if some of the lattice sites remain unoccupied. The number of missing positive ions is equal to the number of missing negative ions, and thus the crystal remains electrically neutral. Unlike a Frenkel defect, a Schottky defect causes a decrease in the density of a substance. This defect is commonly observed in compounds in which the cations and the anions are of almost the same size. Sodium chloride, potassium chloride, and cesium chloride are well-known examples of this defect. The number of Schottky defect in ionic solids is quite significant. For example, in a crystal of sodium chloride, 1 million Schottky pairs per cubic centimeter are noticed. You are already aware that point defects are of three types, namely stoichiometric defects, impurity defects, and non-stoichiometric defects. In the previous module, you studied stoichiometric defects. You will learn about the other two defects in this module. Let's start with impurity defects. You already know that it is almost impossible to obtain a perfectly pure substance. Purification is a costly process. In general, analytical, reagent-grade chemicals are of high purity. Yet, few of them are more than 99.9% pure. This means that a foreign atom, ion, or molecule is present in the crystal. In such a case, we can say that the crystal has an impurity defect. For example, during the crystallization of molten sodium chloride, if it contains a small quantity of strontium chloride, then some of the sites of sodium plus ions are occupied by strontium plus 2 ions. Each strontium plus 2 ion replaces 2 sodium plus ions. Strontium plus 2 occupies the site of one sodium ion and the other site remains vacant, which results in the creation of cationic vacancies in the crystal. The number of cationic vacancies is the same as the number of strontium plus 2 ions present in the crystal. Another similar example is the solid solution of cadmium chloride and silver chloride. The defects that we discussed so far do not disturb the stoichiometry of crystalline substances. However, non-stoichiometric defects affect the stoichiometry of crystalline substances. Let's first define a non-stoichiometric defect. The defect that causes the ratio of the number of cations to anions to be different from that indicated by the ideal chemical formula is known as a non-stoichiometric defect. Non-stoichiometric defects are of two types: metal excess defects and metal deficiency defects. Let's first discuss metal excess defects. A metal excess defect may arise in crystals due to anionic vacancies or the presence of extra cations at the interstitial sites. Metal excess defects that occur due to anionic vacancies can be illustrated by taking sodium chloride as an example. When crystals of sodium chloride are heated in an atmosphere of sodium vapor, the sodium atoms are deposited on the surface of the sodium chloride crystal. The Cl- ions present in the sodium chloride crystals diffuse to the surface of the crystal and combine with the sodium atoms present there to give sodium chloride. This happens because sodium atoms lose electrons to form sodium ions. The electrons so released diffuse into the crystal and occupy the anionic sites created by the diffusion of the chloride ions. As a result, the crystal now has an excess of sodium ions. The anionic sites occupied by unpaired electrons are called F centers. Here, F stands for Farbenzenter, a German word that means color center. The anionic sites occupied by unpaired electrons are called so because they impart color to the crystal. For example, excess of sodium makes sodium chloride yellow. Excess of lithium makes lithium chloride pink. And an excess of potassium makes potassium chloride violet. The reason for this phenomenon is the excitation of the electrons present at the anionic sites of the crystal when they absorb energy from the visible light falling on it. Now let's see how a metal excess defect arises due to the presence of extra cations at the interstitial sites with zinc oxide as an example. Zinc oxide is a white solid at room temperature. On heating, it loses oxygen and turns yellow. Now there is an excess of zinc in the crystal and its formula changes from ZnO to Zn1 plus XO. The excess zinc 2 plus ions move to the interstitial sites and the electrons to the neighboring interstitial sites. The other class of non-stoichiometric defect is metal deficiency defect. This defect may arise due to cationic vacancies. It occurs when positive ions are missing from its crystal lattice. A typical example of this type is FeO, which is mostly found with a composition of Fe 0.95O. It may actually range from Fe 0.93O to Fe 0.960. In crystals of FeO, some Fe2+ cations are missing, and electrical neutrality is maintained by the presence of the required number of Fe3+ ions. Iron sulfide, nickel oxide, and titanium oxide are other examples that have this defect.